Hello everyone, I'm Jianguo from Nanjing University and North China Electric Power University. First of all, I'd like to thank the invitation from the second International Conference on Energy and AI, and I'm honored to give a presentation on the application of machine learning to fuel cell related materials and components. Nowadays, we are facing the challenge of a shortage of fossil fuel and environmental deterioration. At the same time, carbon dioxide emission is one of the big issues the world should deal with together. Many countries announced the timetable for carbon neutral at 2050 or 2060. To achieve such a goals of carbon neutral, the energy system should transit from fossil fuel based to renewable energy based. Hydrogen will be very important in the new energy system when solar or wind energy became the majority of the primary energy supply. That's because hydrogen can be easily converted, stored for a long time, as well as with a highly specific energy supply. With the continuous research and the development of hydrogen energy, the market for the hydrogen energy production, conversion, and storage is rapidly expanding. In addition to be used as a transportation power, it can also be flexibly used in the heating network. In the process of hydrogen energy utilization, the proton exchange membrane fuel cell is also called PEM fuel cells, is the most critical energy conversion devices. A fuel cell is a device that directly converts chemical energy which was stored in hydrogen into electric energy. It has characteristics of high energy conversion efficiency, low noise, and environmental friendly. Although PEM fuel cell has many advantages, the commercialization is still being challenged. The biggest reason is the cost. As shown in the figure, in the PEM fuel cell, the use of precious metal catalysis accounted for 47% of the cost. In order to improve the performance and economy of PEM fuel cell, the core issue is to study how to reduce the amount of platinum in fuel cells, improve the utilization of platinum, and its long-term stability. Our research group has also made exploration on this issue. We have developed platinum, gold, nickel, ternary alloy (ORR) catalysis, as well as nanowire materials. It can greatly improve the catalytic activity while taking into account its stability. In addition, we also made many attempts and achieved some results in the optimization of the preparation process of non-precious metal catalysis, composite protein exchange membrane, and membrane electrode assembles. These results are mainly based on our research experience and analysis of reports in the same field and improve them. Due to the high complexity of the fuel cell systems, its performance is closely related to many important components. It's a good solution to guide experiment work through modeling and prediction, but there are many variables in PEM fuel cells, and the physical and chemical process described by these variables span multi-scales at the same time. For example, the electrochemical reaction on the surface of the catalysis occurs at an atomic level. This requires first principles simulation of the reaction process on the catalyst surface, but the scale of simulation is limited to thousands of atoms. On the micrometer scale, it's necessary to use lattice Boltzmann method or other methods to simulate the two-phase flow to provide insight into gas-liquid transport and diffusion. Further, when membrane electrodes are assembled into PEM fuel cell stack, their dimensions has reached the meter level. In this case, the water management and the thermal management of the liquid water requires research to use the computational fluid dynamic tools for finite element analysis and simulation. Therefore, it's difficult for us to describe such a complex cross-scale device with a unified numerical model. Therefore, in the current scheme, either the catalyst calculation cost will be very expensive, or some important process will be roughly ignored, which will narrow the scope of the application of the model. Therefore, when evaluating and studying how to reduce the amount of platinum in membrane electron assembly and achieving better performance in fuel cells, there are many components and corresponding parameters that need to be considered. We list here some key conditions has been introduced. Faced with so many experimental variables, it's very difficult to conduct material optimization and exploration in actual operating or modeling, because orthogonal screening in such high-dimensional space is unacceptable in terms of cost, and at the same time, the ability of human researchers in such high-dimensional experiment data is very limited. The traditional trial and error paradigm is gradually becoming a bottleneck in the PEM fuel cell research field. Recently, the application of machine learning in the research of energy-related materials has gradually been reported. AI is used as excellent modeling guidance tools in the field of lithium-ion batteries, flow batteries, carbon dioxide to small molecular fuel catalysis and water electrolysis. By learning a large amount of data from experiments or numerical simulation calculations, AI can quickly process complex variables with specific physical and chemical significance and provide researchers with research and development parameters recommendations for obtaining ideal material properties. PEM fuel cell is also a suitable and urgent field for machine learning to bring researcher paradigm innovation. First, PEM fuel cell involving multi-scales, where machine learning can incorporate variables of any scale into a single model. The second point is that the process involved in some variables in PEM fuel cell is sometimes difficult to establish an accurate expression through intuition or through variable equation in numerical simulation. However, data-driven machine learning model can avoid this and learn directly from training data. The third point is that the scope of application of numerical simulation and the description of variables are often less. When there are more variables, the more processes are involved, the more difficult it is to build. However, machine learning model can be processed through some method to process multiple variables and identify the most influential variables and review the rules of interaction between variables. Finally, the introduction of machine learning is expected to provide accurate prediction for experimental and provide recommendation for the best parameters, thereby accelerating the development of high-performance fuel cell materials and components. Here, we propose the use of a machine learning algorithm as an auxiliary mode to accelerate the research and development of platinum reduction and performance improvements. The standard workflow is divided into 4 modules, which is phasor selection, decision modeling, regression modeling, and simulated optimization. The database we used is selected from platinum-based MEA performance, which is 295 papers in the past 17 years, more than 160,000 data points. The first module is to build a classification model for the maximum power density. We use the integrated algorithm XGBoost to achieve the phasor ranking, which is 95% accurate on the test set. After getting the phasor importance ranking and excluding low importance phasor and remodeling, it's found that it still maintains an actual high accurate rate, which proves the reliability of the module phasor ranking result. The purpose of this phasor selection step is to avoid overfitting and high computation cost. By observing the phasor ranking result, we find that the insights of the machine learning model are consistent with the long-term consensus in this field, such as cathode catalyst loading, protein exchange membrane thickness, and catalysis mass activity are considered to be decisive factors. In addition, we also find that the preparation process parameters of MEA often have a greater impact on the final performance of MEA than catalysis parameters. Furthermore, taking the maximum power density as the regression target, we summarize the performance of 34 machine learning algorithms after hyperparameter optimization, compared the prediction accurate error with each other on the test set. And finally, the artificial neural network performs very well. Its prediction error is 0.95, and the mean square error is less than 150 microwatts per cm square, which means it can provide a prediction of less than 10% error for the maximum power density of MEA. In addition, by observing the performance of different algorithms on this dataset, it can be found that integrated algorithm and deep learning are better than traditional machine learning and ordinary generalized linear regression. As the number of phasors increased, deep learning may have greater advantages. Therefore, we apply it to the prediction of the entire IV polarization curves and achieved excellent results on the test set. The last module is simulated optimization, which is based on the prediction model of Module 3. Combined with the best optimization algorithm, which is the particle swarm algorithm, it can allow users to obtain online operation suggestion based on the existing condition to obtain the best MEA performance. Compared with original research and development cycle through trial and error summary, the real experimental data obtained after referring to the AI recommendation for experiments can supplement the training side, making the artificial intelligence involving more accurate so as to obtain higher precise prediction and more valuable research and development parameter, then speed up the RD cycle. In addition to using experiment data or literature report data for data-driven modeling, machine learning can also be used to reduce the computational cost of the numerical simulation. For example, multiphysics simulation can describe the transport of substances in PEMFCS well, but the computation cost is often high. Using machine learning to build a proxy model can greatly reduce the time cost of deploying the model. Therefore, in this work, we have shown how to use the interpretable machine learning to build a multiphysics simulation proxy model and accelerate the design of high-performance MEA. The workflow is first we build an effect and active single cell physics simulation model and verify its effectiveness through experiments, then use it to build a training dataset, and use machine learning to build its high precision proxy model. After getting machine learning as a proxy model, we can take the original complex multiphysics, analyze the proxy model of the field simulation model, and analyze the effect of different experimental variables parameters one by one to help us to confirm which parameters need to be optimized. Finally, we also use the machine learning agent model. The computational cost of this model is much lower than that of experiments and a multiphysics simulation model. Genetic optimization can be used to provide optimization suggestions for production parameters as well as operational parameters, quickly giving performance predictions so as to help us to obtain high-performance membrane electrode products. We use the PDP method and the SHAP method to explore the decision-making of the black box machine learning model for different input characteristics, and found that when the thickness of the catalyst layer is lower than a certain value, it's positively correlated with the output value, and is negatively correlated when it's higher than a certain value. Under constant conditions, the thickness of the catalyst layer is proportional to the platinum loading. Generally speaking, the higher the platinum loading, the better the cell performance. Therefore, artificial intelligence here suggests that there is a gap between the thickness and the loading, a trade-off between the mass transfer and the catalytic rates of oxygen reduction in its own catalyst layer. In addition, we use the artificial neural network proxy module combined with the about genetic optimization method to quickly find the best predictive value of the catalyst layer thickness, which is 4.88 micrometer. The prediction results of the machine learning model are in good agreement with the experiment verification, but it takes only 30 seconds, which is far less than the 5 hours, which it takes to directly use the multiphysics calculations. By this model, we find the prediction for different knife ratio is basically consistent with the volcano law obtained in the experimental. At the same time, the error is very small at the best performance of 30%. From figure D, the preparation of the fuel cell membrane electrode from the slurry to the operation on the fuel cell tester often takes more than 1 day. However, it only takes 0.08 seconds on average to make a prediction by machine learning. Therefore, interpretable model and cost reduction are the biggest advantage of machine learning. At the same time, we obtained the best MEA performance at 0.7 after the optimization through the above AI guidance. Compared to the commercial MEA we purchased in the market, it not only has the better performance, but also requires only half of the platinum loading. Although researchers have made many attempts in low platinum MEA, the use of platinum will always bring higher costs. Therefore, the ultimate solution for reducing the amount of platinum in MEA is the use of a non-noble metal in the cathode. The current focus of right now is on transition metal nitrogen-carbon composite materials. In recent years, rapid progress has been made in this field by screening suitable precursors and optimizing synthesis conditions. However, there are still several major problems in this field. One is that the active site of non-noble metal catalysts are still unclear, and at the same time, their activity is not comparable to that of noble metal catalysis. The other is that their stability in acid is very poor. The most important point is that there is still very little research on the application of non-noble metal catalysts in MEA. That's because non-noble metal catalyst systems are much more complicated than noble metal catalysts, and it's more difficult to describe with simple models. Therefore, as mentioned in the above, non-precious metal MEA is also a very suitable field for machine learning application. For non-precious metal MEA, we first build a more intuitive decision tree. For our task, the classification algorithm divided the record into negative and positive according to the maximum power density. We need to consider visualization while ensuring the accuracy of classification, because it's most important for researchers to check the classification condition of a machine learning algorithm. Decision tree algorithm is one of the best choices. The decision tree divided the boundary conditions by selecting phasor types and the correspondence. So the condition that appeared at the top of the tree, or called the root node, is relatively basic and a common condition. So we can see that the machine learning algorithm is very intelligent and pay attention to nitrogen first. Nitrogen content, humidity, and specific surface area are very critical conditions. Therefore, it can be said that by learning big data, artificial intelligence can learn the consensus reached with the researcher in this field in the past 10 years in a very short period of time. In order to further improve the performance of the generalized ability classification model, we use the most popular XGBoost algorithm in recent years for classification. And the classification accuracy has increased from 86.7% to 91.4%. We use the XGBoost as an important feature index classification algorithm to classify the importance of 26 features. Therefore, the operating conditions in a single cell are often more important than the microscopic composition of the catalysis materials, which also provide the researcher with the opportunity to focus on research and development and pay more attention to the research in the single cell. For regression task, the final result is still that the artificial neural network has the smallest fitting prediction error and the highest performance. After determining that the ANN is the optical algorithm, we applied it to the task of directly predicting the entire area curve. The trained artificial neural network algorithm also have good reproductivity when predict test curves that never been seen before. Therefore, we believe that with the accumulation of experimental data in this field and the expansion of the database, the prediction accuracy will become higher and higher and ultimately achieve the purpose of replacing experiments with high precision. This can greatly shorten the research and development cycle and the developing cost, and use the artificial intelligence to assist in consulting to accelerate the research and development of high-performance non-precious metal MEA. Recently, we found that machine learning model can mine data and discover information that most researchers are least concerned about. As we know, ZIF is an example of non-precious metal ORR catalyst. We have compiled more than 250 data in more than 100 documents, and each record contains 14 catalyst chemical characteristics and 14 material synthesis parameters. By using 9 different algorithms, a total of 252 classification and regression models are constructed and optimized on a database, and the important ranking distribution of different input features are checked through the feature ranking method. It can be found from the figure that different machine learning models consider the paradigm nitrogen species to be very important, which is the same as the long-standing literature in the same field. But to our surprise, when analyzing catalysis synthesis parameters, the parallel time variables in most models is considered to be very important. And in most of the literature we collect, the paralysis time is generally fixed as the constant during the work, and is not discussed. The machine learning model found these rules when compared to experimental records in different documents through data mining. According to the results of big data mining, ORR activity has a huge relationship with the abundance of paradigm nitrogen species, and is closely related to the paralysis time. We explored 17 sets of samples with different paralysis, temperature, and duration, and analyzed the samples through XPS spectra. The paradigm nitrogen species evaluation is obtained by analysis The rule we obtained is in good agreement with the results explained by the machine learning model, with the best predictive performance through the sharp model. That is, when the content of the paradigm nitrogen species is lower, is negatively correlated with the halfway potential, and after a certain value, the paradigm nitrogen species and the halfway potential are positively correlated. Combined with further characterization methods such as thermal gravimetry, we confirm that the change of paradigm nitrogen species corresponds to the three processes. In the initial process, the volatile loss of zinc nitrogen species and the formation of the iron nitrogen species in the ZIF materials are both manifested as paradigm nitrogen species. At this time, the pyrolysis time increased, the overall paradigm nitrogen species in the system decreased, but the iron nitrogen increased. Zinc nitrogen played a decisive role, so the paradigm nitrogen species changed in the opposite trend to the activity. When the pyrolysis time exceeds the top of a volcano, the dominant role is active pyrolysis. At this time, we can find iron through characterization. Nitrogen began to convert to graphitic nitrogen, and the total nitrogen species is continuously lost, resulting in a decrease in active sites. At the same time, it's the iron nitrogen active site that determines the paradigm nitrogen species. The loss of active site and the decrease in apparent activity into a constant trend. At the same time, the first half of the process dominated by zinc nitrogen, the green area becomes shorter as the pyrolysis time rises, which also consistent with the mechanism diagram obtained by analyzing big data and experiments characterization results in the combination with the sharp models. It can be found that machine learning helps us to discover and combine the results of experiments and characterization to discover this important variable that has been ignored by the researchers for a long time, and discover a new material design process worth of attention. In addition, we are currently applying machine learning to parameter optimization in other PEMFCS and other hydrogen-related material, such as the design of PEM electrolyzer and composite PEMs. As shown in the figure, the stability and performance evaluation of PEM often require lots of experimentation and time, and data-driven model can help us pre-evaluating before the experiment. For the solvent selection and the slurry formulation of MEA catalyst air in PEMFCS, we also obtained good results using machine learning modeling. As for the PEM electrolyzer, our model has also achieved high accuracy in the prediction of hydrogen production efficiency and life expectancy, and expected to be used to effectively guide materials development. Finally, there are several perspectives for the future. First of all, in the field of PEM fuel cell stack and system are very expected to be optimized using machine learning technology, especially use the time series modules such as LSTM, real-time diagnosis, and the evaluation of PEM fuel cell in real operation can be achieved, which has a very high practical application value. However, the number of related work is small, mainly because there are few data sets that can be used for machine learning modeling, and the scale is small. Therefore, we hope that in the next stage, the hydrogen energy field can learn from the artificial intelligence field, build a big data sharing platform, and share PEM fuel cell operating data, such as clean energy vehicles or other use cases, with researchers to accelerate the development of better models. This requires further cooperation between industry and academia. At present, The application of machine learning in this field of clean energy is often based on some smaller dataset, and the huge data sources in real industry application are expected to help researchers to develop better models to fit the industry. So finally, I would like to thank the support from the MOST and the Minister of Education from China, and also National Science Foundation of China support, and also thanks the invitation from the conference committee. Also thanks all the students in our group. So most of the work was done by them. Also, there is a recruitment advertisement, as you can see from the first page. So I just transferred from Nanjing University to the North Electric Power University. So there is several positions opened for assistant professor, associate professor, and a full professor. So if you want to know more information, just email me. Thank you, everyone.